In this lesson, we're going to take a look at the Pythagorean Theorem and the converse of the Pythagorean Theorem. So the first one is the actual Pythagorean Theorem, which many of you, I'm pretty sure, have already seen. But what the Pythagorean Theorem states is, if you have a right triangle, which I have here in the green, then what are we going to know? Well, most of you, when you think Pythagorean Theorem, you think the good old a squared plus b squared equal to c squared, and exactly, that's what it is. In terms of the picture equation, there it is. Now, if you want to look at the wordy part of it, if you have that right triangle, then what you see in the red is the words to say that equation. All right? So now, keep that in mind. If you have a right triangle, we can use this formula to find the lengths of missing sides. Remember, A and B are the lengths of the legs, and C is always, always, always the hypotenuse. A and B doesn't matter which one you put where. Doesn't matter if this is the short leg or if this is the short leg. That doesn't matter. It's just right here. Make sure that your C is always the hypotenuse. So what happens is we can use that Pythagorean theorem to help us find missing sides, like I said. We know it's a right triangle, so we can use a squared plus b squared equal to c squared. Now, in my case, I'm going to have the x be the a. So the theorem says square the a, add on, well, b then is going to be 12. Theorem says square the b, and it's going to equal c, and then square. Go through, solve our equation. So we have x squared plus 144 equal to 169. Get rid of the 144. We find out that x squared is equal to 25. And then we can take the square root of both sides. We're going to know that x is going to equal 5. And we'd be done. But wait, what did I forget? Something that I'm going to hound you on over and over again. Don't forget that label. So we found the length of the third side of our right triangle. So the last one we were looking for the length of a leg. Now in this one, notice we're trying to find the length of the hypotenuse. So in this one, do the same thing. Pythagorean theorem is going to work. A this time will be 13. Square it. B is going to be 15. We have to square it. And the C, well, it's our hypotenuse, which is y, so I'm just going to leave it as the variable y. Now I'm going to go through and square 13. So I'm going to end up with 169 plus, and then I have to square 15, 225. Add those together. I'm going to end up with 394. So 394 is equal to y squared. Same thing as last time. Now that we're at this point, now I'm going to go through and I have to take the square root of both sides. Now notice in this one I wanted the approximate value of y and I want the exact value. So I'm going to start with the exact value. Now remember, when you're trying to find the exact, you have to simplify your radicals. Well, simplify it, break it down into its factors. So this one is 2 and 197. Those are the only two factors. Therefore, being I can't take the square root of 2, I can't take the square root of 197, essentially multiply them back together. So we'll be right back to the square root of 394. And then my label on this, same label as what was up here, b. That would be the exact value of y. Now, to get your approximate value, just go ahead and punch it on your calculator. I'm going to do that right now. Take the square root of 394. That's going to come out to be approximately 19 point, a few decimal places, 85. That's supposed to be an 8. B. My approximate, excuse me, value of y. So something, just kind of a little side note here. If we would have had something, let me just get a new page. Say it would have been the square root of 394. Say it would have come out to be the square root of, I'm going to go something a little smaller, 20, and we have to simplify that. That's looking at, now when I talk about factoring it, I look at 2 times 10. Factors of 10 would be 2 times 5. So there are all my prime factors of 20. Now what I look at is right here. 2 times 2 is 4, and the square root of 4 is 2. Now the reason I do it like this is because if I have pairs of numbers, see I had two two 2's underneath the radical, well, that comes out to be just one 2 on the outside, and then square root of 5. So the square root of 20 is equal to 2 times the square root of 5. Simplifying a radical. Now you have the exact value instead of the approximate. Now the converse of the Pythagorean theorem, this one's also true. So now you go backwards the other way. The last one said, the Pythagorean theorem said if it's a right triangle, then this little equation works. Well, the converse says if the equation works, then it's a right triangle. So in other words, if you have two sides in a triangle, you square them and add them together, and that number is equal to the third side, the longest side squared, then you know it has to be a right triangle. And the reason this one's helpful is because when you get into something like this, if it asks you to find out if it's a right triangle or not, just given 3 side lengths, we're going to be able to do that. So we can take our 3 numbers, throw them into that little equation of a squared plus b squared equal to c squared. The only part you have to watch for is c. That always has to be the biggest number. The other two, it doesn't matter. So what I like to do is just throw them in alphabetical order, or not alphabetical, sorry, numerical order. So I'd have 21 squared plus 28 squared, and then equals, or I'm going to put a big question mark here because I don't know if it's equal or not, to 35 squared. Well, now go ahead and square all your numbers. So this is 441. 28 squared is 784. And now if I add those two together, I end up with 1,225. If I square 35, I know that's 1,225. These numbers are equal, which means this was true, which means those 3 numbers will make a right triangle. So do the following side lengths make a right triangle? Yes, those will make a right triangle. Now, if this one would have come out to be 1,224, then my answer would have been, no, it's not a triangle. Or if this would have been something else. If they're not equal, not a right triangle. If they are equal, it is a right triangle. Now, Pythagorean triple. Pythagorean triples are kind of cool because there are 3 numbers, hence the triple, that satisfy the Pythagorean theorem, but those 3 numbers also are whole numbers. So there's 2 parts to it. They have to be whole numbers, and they have to satisfy that equation. So probably the most famous Pythagorean theorem is the 3, 4, 5. 3 squared plus 4 squared, yes, it does equal 5 squared. Now, there are other Pythagorean triples out there, and there's many, many of them. One way to find another Pythagorean triple is just take one that you already know and multiply everything by a number, like multiply everything in the 3, 4, 5 by 2. So the 6, 8, 10 would be another set of Pythagorean triples. You can multiply it by 3, so then you end up with your 9, 12, 15. Those a lot of times are referred to as one family of Pythagorean triples, where the 3, 4, 5 would be the parent. There was another Pythagorean triple within this lesson. Wondering if you can think back to what that was. But if you forgot, the first triangle that we're looking for the missing side in, 5, 12, 13. That's another Pythagorean triple. And again, you could go through and multiply that by 2, 3, any whole number, and you get another Pythagorean triple. Are there more? Yes, there are. There are many, many more Pythagorean triples. See if you can find one. And then there's your assignment.